Hello, 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 and welcome everyone to our Thursday night edition of the Chegg Gen Chem Office Hour. I'm super excited to be here with you all. My name is Dr. J, or you can follow me at Gen Chem with Dr. J. I'm really excited to be partnering with Chegg to offer this Chem Office Hour. It's a great way for you all to learn more about the different topics that you're studying, get some questions answered, and do help explore all the resources that they have. So a little bit about me before we get started as we wait for people to roll onto our live stream. I have been teaching some form of chemistry for the last almost 2 decades. But I also have a PhD in analytical chemistry and run a nonprofit that introduces K through 12 students to STEM, which is science, technology, engineering, and math concepts through exciting hands-on activities. I actually launched this platform, Gen Chem with Dr. J, a few years ago to support students around the world as they navigate their own chemistry journeys. I'm super excited to partner with Chegg to host tonight's office hour, and I've really enjoyed the last few weeks getting to talk to students, answer questions, and help you all feel more confident as you take your classes. So for those of you that might be new to Chegg, they are here to make your academic journey a bit smoother. They have a ton of resources to help you get through school, like online study help, expert Q&A with step-by-step solutions, writing support, and a whole bunch more. And they offer all types of live office hours all throughout the week. So you can check out that QR code that's in the top left corner to see the full schedule of different office hours that are offered. So for those of you that have never joined one of the lives before, welcome. And for those of you that have been here before, welcome back. I'm excited to help you all as we think about some of these different chemistry concepts. So as we get ready to get into tonight's live, we're going to do it the same way. I want to hear from you. I want to make sure I'm answering questions that are relevant to the coursework that you're doing. If you have questions from last time, if you learned something in class this week that you're not really clear on, go ahead and drop those in the comments. We're going to try to answer as many of those as possible throughout tonight's session. And if whatever we don't get to tonight, we'll be back at it again next week. Okay? So we always like to make sure we are set up for success whenever we're doing any of these office hours. So if you're going to be following along with me for doing some problems, go ahead and make sure you have a pencil or a pen nearby and some paper or a notebook that you're capturing your notes in. You want to make sure that you have a calculator nearby. And so I have a scientific calculator. Your scientific calculator should have the ability to do exponents, and make sure that you have that EE button, or you can do that times 10 raised to a power button. And so we're going to use these a lot today. And then we're also going to need our periodic tables. And so your periodic table is going to be super helpful as we are doing some of these problems. Okay. So I have a couple of preloaded questions to kick us off, get us warmed up, and then I'll be answering some questions. So if you have questions, add them to the chat right now, and we'll be sure to get to them as we go through. Okay. And so I wanted to start off this office hour answering a question from last week, which someone posed a question all around formal charges. You know, what do we use formal charges for, and how do you do them? Okay. And so formal charges are a way that we can evaluate or look at different Lewis structures that we come up with for different compounds that we are tasked with in a class. Okay. And so sometimes you might have a compound that's given to you, and you can come up with multiple structures for how you would make the Lewis structure. And so the formal charges are a way for us to figure out which one is the better structure. Okay. And so let's try this problem together. Here I'm asking you all to draw first 2 possible Lewis structures for the following compound, SeOF2. And then we're going to calculate formal charges that are found in both structures. Okay. So remember, when we're doing Lewis structures, you have to first ask yourself, well, what element goes in the center? All right. And you're going to choose the element that is the least electronegative. All right. So electronegativity is that ability for an atom to pull electrons towards it. And so the least electronegative atom is the element that's furthest away from fluorine. Fluorine is actually our most electronegative atom. And so if we look at where oxygen, which is right here, versus selenium, which is here, are found on your periodic table, you can see that selenium is the furthest. And so that's going to be what goes in the center. So I'm just going to go ahead and put my selenium in the center. And then to start, I'm just going to arrange the rest of the atoms around it. And I like to do it symmetrically to start. We can always revise that later, but just start with it being more symmetrical, okay? Once you have your electrons, remember we said we're going to do two different structures. So we can go ahead and start by just calling out two different structures because we know we're going to be doing that. So once you have your atoms in place, you then are going to give each element its valence electrons to start. And so remember, valence electrons, we find those based off of the column that things are found in, or what's called our group number. And that group number for your main group elements, column 1 and 2, and then 3 through 8, are going to be the same as the group number. So selenium is found in group 6, and so it will get 6 electrons. And so to start, I just like to always put my 6 on there. I'll put at least 3 towards the fluorines and the oxygen. And then I'm just going to come back and put the remainder on there somewhere. Now, those electrons might move, but to start, I want to make sure that I have all the electrons accounted for. Now, fluorine is a group 7. And so I'm going to put at least 1 going towards selenium and then the remainder around the fluorine, like so. And again, remember, electrons like to be in pairs. And so if they're not bonding, try to make them as pairs. I'm using X's and O's just so it's easy to see what I'm doing. You can use dots, stars, circles, whatever you want. All right, so this fluorine over here also gets 7. Okay. And oxygen, if we look, is a group 6, so it also will get 6. And so I'm going to put 6 electrons around it. Okay. I'm going to do the same thing on the second version, just because I know those initial valence electrons aren't going to change, right? So again, I'm going to give selenium at 6, fluorine gets 7, oxygen will also get 6, okay? And again, X's and O's are just so that it's easy for you all to follow along, okay? All right, so now let's focus on one structure now. Let's focus on the left one. And so now, once you've given each element its valence electrons, our first rule is to go through and make one set of single bonds that are connecting the central atom to those outside atoms, okay? And then we step back and evaluate. And so I'm going to make a bond there, a bond there, and a bond here, okay? And I count by just doing that first round of bonds. I know for whatever reason, students love double bonds, and y'all like to throw double bonds everywhere. But before you start throwing double bonds everywhere, step back and count. Around our fluorine, we now have 7 that it started with, plus now it's a covalent bond, so it's sharing that one with the selenium. And so around this fluorine, there are 8 electrons. Similar with the one on the left-hand side, we have 8, 7 of its own, plus sharing 1 more. Count the oxygen. Oxygen has 6 of its own, plus is sharing 1 more. So right now, oxygen has 7. And selenium, remember, started with 6. It's now sharing 3 more. And so it has a total of 9. Okay. And so now we're at a crossroads, right? We got to figure out how can we get the proper number of electrons around each of these atoms. Remember, most atoms are most comfortable whenever they have an octet. Octet meaning 8 electrons surrounding it. And that could be through sharing those electrons as well. And so we do have a certain group of elements that are able to have more than 8. Okay, and that's called the octet expansion rule. And that's any element that exists that lies in row 3, period 3, or lower, meaning period 3, 4, 5, 6, 7, 8. Okay. And so we check and see that, yes, selenium is in period 4. So that means that it could have more than 8 electrons around it. Okay. And so with that in mind, we're going to think about what can we do? Is there a way we can get just 8 electrons around selenium? Okay. So what you should be saying is, well, selenium has an extra one in this case. Oxygen is missing one. Could we just give it to it? And yeah, actually you could. All right. Because selenium has that extra electron that was not bound or in a lone pair, we could actually move that up to the oxygen. And by doing that, that now gives our oxygen 8 and our selenium now has 8 as well. And so for all purposes, this could be a reasonable structure. But we could have done something else as well. And so I'm going to focus on the right side now. Again, same thing, do one set of bonds first. So our counts would be the same as that previous version. So we had 8 here, 8, 7, and 9. So in the left-hand version, we actually moved that electron from selenium up to oxygen so that we could make the octet that way. But the other thing we could have done is instead of giving the electron to oxygen, we could have repositioned it so that instead of giving it to it, it now shares it with selenium instead through a double bond. Okay. Now, when we count here, we see that oxygen ends up with 8 electrons. So that's good, the octet. Selenium now, however, if you count, there are 8 bonded electrons plus 2 more lone electrons, which gives us 10. And so you should be like, oh my goodness, there's more than 8. Is this possible? Well, yeah, remember octet expansion, period 3 and lower can have more than 8 electrons in it. Okay, so that works. All right. All right. And so now this is where the formal charges come into play. The formal charge calculation is going to help us to figure out which of these structures, this is considered a resonance structure, is the better structure. Okay. And these are resonance because notice the atoms are not moving positions. They're the exact same positions, but there's this pair of electrons that's either a double bond between selenium and oxygen or a lone pair on just the oxygen. And so the formal charge, what we're going to do is a quick calculation, which involves using, so the formal charge calculation, I'll put it here at the top. So the formal charge calculation, we're going to take the valence electrons that something has, that the atom has, minus the lone electrons, okay, minus 1/2 of the bonding electrons that are connected to it, okay? And so what we'll end up doing is doing a calculation for each of these atoms and then adding them up to see which one makes the best charge, okay? So let's take selenium first, okay? So for selenium, remember the valence electrons were 6 valence electrons minus the lone electrons, which you only look at how many lone electrons are on the selenium, which right now is just 2, okay? So minus 2 minus 1/2 of the bonding electrons. Now, this is all the electrons that it's bonded, that are connected to it by bonds. So that's 1, 2, 3, 4, 5, 6 total. So 1/2 of 6, or you could just do 3, okay? Okay. And so when we do that math, that gives us 6 minus 2 minus 3 gives us positive 1. Okay. Let's do fluorine. Fluorine has 7 valence electrons minus 6 lone pairs. Excuse me, 6 lone electrons, not pairs, minus 1/2 of the 2 electrons that are connected to it, that are shared. So that gives me 7 minus 6 minus 1. That gives me 0. Since both fluorines are exactly the same, have the same number of lone electrons and bonding electrons, I don't need to do this calculation twice. I can just simply say times 2. So that still equals 0 for that. Okay. If the fluorines look different, we would have to do two separate calculations. And then we're going to take oxygen and we're going to say 6 for its valence minus 6 lone electrons that are on it minus 1/2 of the bonding electrons that are connected to it. So that's 2 of them. 6 minus 6 minus 1 gives us -1. Now, when we add all of that up, +1 plus 0 plus -1, the formal charges should add up to the charge of the compound. And so we see it does add up to 0. It's a neutral compound. So that means that this is a reasonable structure. But is it the best structure? Okay. So to compare, we're going to do the same calculations for the other version that we created. All right. And so I'm seeing a lot of shout outs there. Hey, Latisse, how you doing? And so we're going to take, for our selenium in this case, we're going to take selenium and we're going to do, again, the valence electrons, which is 6, minus lone electrons. So on here, there's only 2, minus 1/2 of the bonding electrons. So there's 8 electrons connected to it through the bonds. So that gives us 6 minus 2 minus 1/2 of 8, which is 4. So 6 minus 2 minus 4 equals 0. Our fluorines should be the same, right? Because it's the same bonding pattern. So we have 7 minus 6 lone electrons minus 1/2 of the 2 that are connected to it. That gives me 0. And there's 2 of them, so times 2 still equals 0. And then our oxygen. Oxygen here will be 6 valence minus 4 lone electrons minus 1/2 of the bonding. So there's 4 bonding electrons connected to it. So 6 minus 4 minus 1/2 of 4 is 2 equals 0. So our total here is 0. So again, the sum of the formal charges adds up to the charge of the compound. So it's a reasonable structure. So then which is the better structure, right? The better structure is going to have a few things. One, the better structure will have the fewest number of formal charges. Okay. And so we can see in the second compound that we came up with, there are no formal charges. We have 0, 0, 0 versus the first version, we had a +1 and we had a -1. Okay. So that's one reason that the second version's better. Again, the sum of the formal charges have to add up to 0. So it happens in both of those. So that means they're both reasonable. But then the last rule is the fact that if there is a negative formal charge that comes out through the process, that negative formal charge should end up on the most electronegative atom in your compound. Well, look at the first version. Look at this one. Look at the one on the left. We got a -1 formal charge. However, it's on the oxygen, not the fluorine. Remember, fluorine is your most electronegative atom. So because there are fewer formal charges in the second version, because the negative in the first version did not end up on the most electronegative atom, that would tell us that this one is the better structure. Okay. And so I know that was a lot of steps there, but I wanted to spend some time with that because we ended our office hour last week with that. But again, draw your Lewis structure, do the calculation, and you're going to be looking for those rules. Formal charges should add up to the overall charge of the compound. You're looking for the fewest number of formal charges overall. And if you have a negative formal charge, it should add up on the most electronegative atom in that compound. Okay. All right. So I'm seeing a lot of questions coming through. Awesome, awesome, awesome. So I'm going to take a few questions from our classroom. And so I'm seeing a few questions that are asking about polarity and dipole moments. So I'm going to address those. And so I see DC, you've asked, can you explain the difference between nonpolar, polar, and ionic bonds? And then I saw somebody else, where was it at, that said, Robert wanted to know about dipole moments as well. And so I'm going to talk a little bit about that. And then there was one other one. Yep, I see somebody else using polarity. All right, so let's get into polarity, dipole moments, etc. Okay, and so we're going to talk about the difference between nonpolar, polar, and a ionic compound, and then I'll weave in the dipole piece to it. Okay, and so let's look at three different compounds and compare them. Okay, so we could have NaCl. We could have HCl and Cl2. Okay. So let's talk about the main difference between ionic compounds and molecular compounds first. Okay. So ionic compounds, or actually ionic compounds and covalent bonds, ionic bonds and covalent bonds. So ionic bonding, when you have ionic bonding, you are transferring electrons, okay? Your metal or your cation is going to be losing electrons, and your nonmetal or your anion is going to be gaining electrons. Because you're able to lose electrons, the metal takes on a positive charge, which is why we call it a cation, and your nonmetal typically receives the electron, and so it becomes the negative charge, an anion. And so in this case, we're not, just like in that previous example where I showed they were sharing electrons, we're not sharing electrons here, okay? So what happens in an ionic compound, and again, you'll know you have an ionic compound when there's a metal present. So sodium would have started off with one valence electron. It's a group 1 metal. Chlorine would have 7 valence electrons. It's group 7. Now, in ionic compounds, they're not sharing an electron. That's incorrect, okay? What happens is that chlorine is actually able to take that electron from sodium, or sodium is willing to give up that electron, right? And so because sodium loses that electron, it takes on a positive charge, and your chlorine takes on a negative charge, okay? And so in ionic compounds, in ionic bonding, you're transferring electrons, okay? There's all of your electrons now are on that chlorine. Your sodium has this empty valence shell, and that positive area and that negative area are what are attracted to one another, okay? So this is ionic, okay? Now, covalent bonding, covalent, co means together, right? Valent. So those valence electrons are being shared between those atoms, okay? Now, this is going to happen when you have two nonmetals or a semimetal and a nonmetal binding together, okay? And so in the case of like HCl, you have hydrogen and you have chlorine. So hydrogen, again, has its 1 electron. Chlorine has its 7. And so they actually share this electron, okay? And in Cl2, the same thing would happen. You're sharing electrons, okay? So we have chlorine. We have 2 chlorines. Each chlorine would have its 7. Okay? And again, they're going to share, trying to get that octet, okay? Octet. You're getting that 8 because it started with 7, and I'm sharing 1 more, okay? Hydrogen's an exception. It only needs a duet. It only needs 2 electrons. It doesn't have the space for the full 8, okay? Now, both of these are considered covalent because they are sharing their electrons, okay? However, one of these is considered to be polar, and one of them is nonpolar, okay? And so what polarity has to do with is there uneven sharing of electrons, okay? Think of it kind of like tug of war. Imagine that you have like a really small person on one side of a rope and a really big person on another side of the rope. And they're pulling on this. They're both sharing that rope, but one is able to pull it more towards them than the other. Okay. Well, that's what's happening when we have atoms that have a big difference in their electronegativity. Again, electronegativity is that ability to pull electrons towards the atom. Okay. And so when you have elements, two different elements primarily, with a significant difference in electronegativities, you're going to end up with uneven sharing of electrons. They're still sharing, but I'm pulling that rope a lot closer to me. Okay. And so what happens is, instead of, like in the case of Cl2, where they're both the same, right? They both have the same electronegativity. So the electron cloud that's surrounding chlorine would be very symmetrical. It'd be even. Whereas in HCl, that chlorine is able to pull those electrons more towards its side. And so HCl, this would be considered a polar compound, okay, because you have this is sharing, but it's uneven, versus Cl2 would be a nonpolar compound. Okay, so again, polar is about uneven sharing, uneven distribution of your electrons. All right. Now, getting to the question, I think Robert had asked about dipole moments. So now the dipole moment is looking at, well, what direction is that uneven sharing happening? Okay. And so how we reflect our dipole, you draw this arrow with like a positive end, and the arrow points in the direction of where the electrons are shifting towards. And you can kind of think of it like the positive, the plus sign at the top of the arrow is kind of like the more positive region. All right, so there would be a not a full ion like here. So that's an ion, right? Because I've gotten rid of my electron. This hydrogen area has what's called a pseudo positive region. All right, so we draw the sigma symbol. And over here, this would be a pseudo negative region. And so that positive and negative region that's created because from this uneven sharing is what allows things like water, which has this dipole moment, to dissolve salt because of that interaction between the polar ends of the compound and the charged species. Okay. And so again, ionic, we're transferring our electrons. Typically is going to happen when you have a metal present. Your metal becomes positive, your non-metal becomes negative, and they're attracted by that positive and negative interaction. For a polar compound, you typically metal, non-metal, 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 semi-metal, and there is, polar bond. This uneven sharing between the elements. And then a non-polar is whenever you have even sharing of those electrons. Okay. So I hope that helped you understand the difference between ionic, polar, and non-polar. Okay. All right. I'm just scrolling through to see a few questions. Yep, I'm seeing a few people. Hey, Danny. All right. And so I'm going to keep going through again. Keep dropping your questions in the chat. I'm going to answer a few more that were received before here. Can there be more than a triple bond? Typically, you don't really see too many more than a triple bond, and that just has to deal with, again, that rule about that octet rule. What's going to make them the most stable? And so triple bonds are less common. You won't really see anything much higher than that. Okay. Hey, Wakiba, I'm seeing some people come in. All right, let's see. So do I do sessions for physical chemistry? It's so hard. I agree. It was hard when I was in school too. I unfortunately don't do office hours, but I would encourage you to check the schedule that's on the top left corner and see if there is a PChem class that's available for you all. Okay. All right. So let's keep going on. I actually want to do one other problem while we're on this polar and nonpolar, because it goes back to this what's a dipole question that I just saw come in. All right. And let me get another blank one. And that is around whether or not an entire compound will be polar or not. So what I just showed you in that previous example was dealing with a single bond, right? So Cl to Cl, or HCl, or NaCl, I think was the other one I did. But occasionally we might be given a compound instead of just a bond and ask for if it's polar or not. And so I want to do two quick examples for you. And so something like SF6 versus an H2O. Okay. And, the question would be, would these be polar or nonpolar molecules? Okay. So polar or nonpolar. Okay. So you can put your guesses in the chat whether or not you think SF6 and H2O would be polar or nonpolar. Okay. And I'll show you how we'll go about doing that. Okay. And so when we're looking to see if a compound, an overall compound, is polar or nonpolar, a couple steps we have to do. First, you need to think about, well, what does that Lewis structure look like? Because the Lewis structure is going to ultimately allow us to figure out what the electron geometry is, and then really the molecular geometry, which is going to be what we base this question off of. And so if we take SF6, that would end up having sulfur in the middle. It's our least electronegative atom. We would put our fluorines around it as such. So 6 fluorines. I give each atom its valence electrons. So sulfur has 6 valence electrons. And so I'm going to give 6 here. All right. And then fluorine gets its 7. So again, I'm using X's and O's. Makes it nice and easy for us just to see what's going on. So each fluorine gets 7. Okay. And again, when I'm doing these, I try to put that single electron towards the center, so it's just easy for me to be able to make my bonds. Okay. And then we go through, we make one set of single bonds first, like so. Okay. And then we step back and count. Around each fluorine, we can see that they each have 6 lone electrons, and then 2 bonding electrons. So that's 8 around each of those. So their octet is set. And then sulfur, if we count around it, there are 12 different electrons that are there. You should always cross-check. I got 12. Can it have 12? Well, it's in period 3. And so we can see that, yes, the octet expansion would apply. That means that there are some empty d orbitals that we're able to have those extra electrons in. All right. And so then once you have the Lewis structure, we can get the electron geometry. And so the electron geometry looks at how many lone pairs and bonding regions are around the central atom, and then we are able to determine a shape from there. Around the central atom, sulfur, there are no lone pairs, but there are 6 bonding regions, and that 6 tells us that this will have an octahedral shape. And so shape-wise, it'll look like so, where we have fluorines that are in the plane coming. So imagine what we're drawing here is this 3D structure. Those fluorines are basically jumping out of the page at us. The ones that I'm drawing now with the dash line means they're behind the page, if you will. And then there's something up top and something on the bottom. Okay, so they're making this kind of 8-sided diamond shape, what's called an octahedron. Because there are no lone pairs, the molecular geometry will be the same. So this actually is the molecular geometry and the molecular and the electron geometry. And so the question about would this be polar or non-polar, for the overall compound, you need a couple of things. So first, you need to have polar bonds present. So we have sulfur and it's bonding to all these fluorines. So each of those sulfur to fluorine bonds would be polar. Each individual bond is a polar bond because they're two different elements. They're sharing the electrons unevenly. Then the second test that we have to do is, well, overall, when we look at the central atom, is it being pulled symmetrically around it? And because each of those fluorines is all fluorine around it, in every position that it could be pulled, it's being pulled and being pulled evenly, we would actually say that this is nonpolar. Okay, even though there are polar bonds. Okay. All right. Yep, and I see, yep, Bong, you got that one correct. And then H2O, yeah, so H2O, Lewis structure, we would have our oxygen in the center. We would start with 2 hydrogens. Oxygen gets 6 valence electrons. Each hydrogen gets 1. Make your bonding, okay? Now, it's really important to not try to figure out the polarity off of the Lewis structure for the overall compound, because the Lewis structure is not drawn in a way to reflect the actual shape of it, okay? Right now, the Lewis structure is drawn as a 2D flat dimensional, but the electron geometry and molecular are representing it as a 3-dimensional, okay? And so, oh my goodness, Ethan, you're jumping ahead. You're getting to sigma bonds, and we can talk about sigma bonds and pi bonds. I love it. And so here, because we have 2 lone electrons, 2 bonding regions, this would actually be an electron geometry of tetrahedral. And so we would have our oxygens, we would have a lone pair, 2 lone pairs, and then we have our hydrogens, one coming out at us, one going away from us. And so then the molecular geometry would just be the molecule as it remains. Okay. And so what we end up with is this bent shape. Because it's bent, we don't have that pull happening on the other side of the oxygen where those lone pairs were, right? And so this, because we don't have the symmetry around this central atom, this would be considered polar. And it would have a dipole moment, right, going towards in the direction of that oxygen, okay? And so this oxygen area would have a pseudo-negative region, and around these hydrogens, there would be a pseudo-positive region. Okay, so dipole, going back to that question, di means 2. It's 2 different regions that exist here. Okay, and so hopefully that helps as you are thinking about that. Okay, all right. Let's get into some more questions here. How does a bond polarity affect the properties of molecules? So great question, Leticia. I'll stick with that question just because it's all kind of tied in here. And so when we think about whether or not something will dissolve, okay, have you ever heard of the saying, like dissolves like? Okay. Or more importantly, have you ever taken water and tried to mix some oil in it? Which you've likely seen if you've done that, or maybe you didn't do it intentionally, or even if you've had like a makeup remover, like the makeup remover that has the micelles in it, right? I won't say the name, but it has the micelles in it. You see this layer that forms between the water and the oil. Well, polarity impacts whether or not things are going to want to dissolve and create solutions with one another. So that saying, like dissolves like, polar molecules like to be around other polar molecules, whereas nonpolar like to be around other nonpolar. So if we try to take oil, which is a more nonpolar, and water and mix them, they don't like to mix. And that's because they have two different these two different properties. Okay. Now, polar and ionic compounds can mix because of those charges. Then that's that pseudo charged area that is created. So that's why salt, which is an ionic compound, can dissolve in water because of those properties. And so this polarity and nonpolar, this is all around us. This is like the premise behind how like makeup remover works and how nail polish remover works. The reason that like I wear nail polish, the reason it doesn't come off in the water is because the nail polish itself is not the same polarity as the water. And so you need something that's less polar to remove it, which is why we use things like acetone or ethyl acetate to remove it. And so those are some more real life examples as to when polar and non-polar properties show up. Okay, great question. Great question. All right. All right. I'm seeing from Bong NW or Bong NWI a question about nomenclature. So, do I have any tips for studying nomenclature? Yes, actually, I have a lot of tips for that. And so we'll just get another blank page here. So nomenclature. Nomenclature is how we name things. Okay. And so when you're naming things, it also goes back to this idea of, do I have ionic compounds or do I have molecular compounds? Ionic compounds have a certain way that we name them. Molecular compounds have another way that we name them. Okay. And so, again, when we're dealing with molecular compounds, again, those are those elements, or excuse me, compounds that don't have a metal present. When you're naming binary, so this nomenclature that I'm about to walk you through is for binary compounds. So binary meaning two elements present. When you have binary molecular compounds, we list, there's kind of four positions that you're dealing with, okay, for the naming properties. This first position represents a prefix. Okay. And that prefix is telling us how many of one of the elements is present, the first element that's in your compound. Okay. You then list the first element that's found in the compound. You then have another prefix that describes the second element. And then you would put the second element plus the IDE ending. Okay. And so those prefixes are prefixes. Your professor likely gave you a list of them, or you can Google, go to Dr. Google. But your prefixes are like 1 for mono, 2 for di, 3 tri, 4 tetra, 5 penta, so forth. Okay. Now, very, very important in this position here, the first position, you never use the mono prefix. Okay. You can use any other prefix there, but you don't use mono. Okay. You can use di, tri, hepta, any of those, but never mono. You can use mono in the second example. So like, for instance, anytime we see CO, we would always name this carbon monoxide. Okay. So again, we're not saying the mono there. Mono is considered to be redundant in that first position if you would have to apply it. We only have one carbon in the second, or excuse me, one oxygen in the second as the second element. So then that's the mon prefix and then oxide, versus something like CO2, that would be carbon dioxide. Or if we had something like C2Cl2, well, this would be dicarbon. Actually, C2, let's do Cl4. C2Cl4 would be dicarbon tetrachloride. Okay. And so again, the di is telling me how many carbons I have. The tetra is telling me how many chlorines I have. Okay. And so this is the naming format when we're dealing with binary molecular compounds. Okay. Now, when you're dealing with ionic compounds have a different naming format. Ionic compounds, we're not using those prefixes in this manner. Okay. Ionic compounds, what we're reporting out is really considered to be the simplest whole number ratio of the ions that are present in that compound. And so rather than listing a prefix, right, because we don't have this singular molecule that's there, we're going to be referring to what cations are present, what's those positive ions that are present, the anion that's present, excuse me. And then if we have an ion, a cation that can have multiple charges, we have to explain that charge as well. Okay. And so when you're naming, you take the cation first, which is your metal for the most part. Again, that's 99% true. I'll show you one example when it's not a metal present, but it's still an ionic compound. You then would take the anion and you would add the IDE ending, with the exception of if you have a polyatomic ion present, you don't add the IDE ending, you just write the polyatomic ion. So I'll just write anion or the polyatomic ion. Okay. And so this format works. We follow that format as long as you have a metal with a fixed charge. Okay. So your fixed element, fixed metal charges, that is your group 1, group 2, silver, which is +1, zinc, +2, scandium, +2, and aluminum, +3. Okay. If you have any other metal present besides one of those fixed, then you have to actually, you're following the same format where we're going to name the cation first. You'll still name the anion as well, or the polyatomic, whatever's present. But now in Roman numerals, you're putting the charge of the metal or of the cation. Okay. In Roman numerals. All right. So for instance, if we had CuO, okay, CuO, you would first check on your periodic table. Again, let me see. Go ahead and try to name this one in the chat. But I'll walk you through the steps. So Cu is copper. If you find copper on your periodic table, it is found in the transition elements. And so copper is not one of our fixed metals. And so we need to know the charge of it. How do we find the charge? Well, we can look at what would the charge of the oxygen be and help us to use that to figure out the charge of the copper. So our oxygen is a group 6, would have a -2 charge. To balance that out, that means copper must be a +2 charge. And so the name here would be copper 2 oxide. Okay. Copper 2 oxide. Try to clear up some more space here for us. All right. And we'll do one more. Let's say we had Na2SO4. Okay, wait a minute. Got a little bit tricky. We got 3 letters here. What's going on here? Well, SO4, that is actually a polyatomic ion. So again, poly means many, atomic, so many atoms, ion with a charge. So polyatomic ion just means many atoms with a charge, right? And so again, your teacher likely gave you a table that has a bunch of polyatomic ions. And so you need to memorize those. I stressed last week how easy it is to memorize them if you use like flashcards or index cards. Put the name of the polyatomic on the front, put the symbol or the formula and the charge on the back, and just pull those out every once in a while just to quiz yourself. You need to know those. I cannot stress how much you need to know those. Okay. And so here we'll take, when we're naming, we still follow those same rules though. So I check, do I have a metal? Yes, I have sodium. Sodium is a group 1 metal. So that means I don't need to worry about stating its charge because its charge is always the same. So there's no reason for me to have to state it. All right. And then I check, well, what polyatomic ion do I have? SO4 with a -2 charge, that is sulfate. And so when I name this would just be sodium sulfate. Okay. So I hope that helped with your nomenclature question. Okay. All right. I think we got time. We're going to try to get to one more question. And I did have a question that I wanted to work through. That was somebody had asked earlier a question online today about molarity. And so I wanted to do a molarity question for you all. And then we might have time for maybe one more, depending on how quickly we do this. All right, so let's talk about molarity. So molarity is the unit that we use when we're trying to measure how strong of a solution that we've prepared is, okay? And so solution, remember, a solution is something that has two things present. There was a solvent, so some larger amount of substance, and a solute, maybe a smaller amount of substance that we added into there, okay? And we mix it all up. All right, again, think about like if I had a bunch of water and I had some salt. My water is my solvent. Water is considered to be your universal solvent in chemistry. And my solute in this example would be my salt. I'm going to put my salt in my water and it's going to get dissolved. And so the concentration is going to tell me, well, how strong, how much salt did I actually have in there? Okay. And we use this concept of molarity as a measure. Okay. So molarity, the formula for molarity is equal to the moles of your solute compared to the volume in liters of your solution. Okay. And so here, this is again a place where you're going to hear moles throughout this class nonstop. Okay. And so it's important to remember, how do we get to moles? And I've shown you all my mole island tip that I love to use that helps you to figure out how do I get from grams to moles or other values, other units to moles. And so in this question here, it's asking us to find the molarity of a solution that is 25.5 grams of KBr dissolved in 1.75 liters of solution. Okay. And so for this particular problem, well, we have the volume, right? This represents our volume of solution. I'm solving for my molarity, so that's my unknown. And I'm given this information about grams. Well, how does that help us? Well, we do know a direct relationship between the grams of something and its moles. Remember, we talked about a couple classes or office hours ago, our molar mass, which is found from the masses on the periodic table, is equal to 1 mole of that compound, okay? And so what we're going to need to do in this problem is to first go from grams of KBr, potassium bromide, to moles of KBr, okay? And then we'll be able to plug into, can't write today, into this calculation, okay? And so if the molar mass isn't given to you, you're going to have to calculate that. And so you go to your periodic table, and I see potassium. Potassium is 39.098 grams. And then bromine is equal to 79.904. Okay. And so we're going to add those two together. And so we got 39.098 plus 79.904. And that gives me 119.002. And this will be grams per mole. Okay, so this is our molar mass. Okay. And so to get our moles, we're going to do that given and find format. And so we started with 25.5 grams of KBr. And I want to get to moles. So if I want to solve for moles, that means I need moles to end up on the top here. And on the bottom, I'm going to put my grams of KBr, and that's going to allow my units to cancel out. I'm going to plug in my value of 119. Oh, go back. 119.002. It's that many grams per 1 mole. And I plug that into my calculator. So I have 25.5 divided by 119.002. And that gives me 0.214 moles, okay, of KBr. And then the last step we're going to do is our moles divided by the volume. And again, always cross-check. It is in liters. If it wasn't in liters, we would do that conversion first. So divided by 1.75, and that gets us 0.122. And the units would be either moles per liter or 0.122 capital M of KBr. Okay. And so I hope that cleared up some questions for you as you all are thinking about molarity and how we're doing that. And so let me see, just try to see if there's any other quick questions I could respond to. But yeah, so Chegg has a ton of resources available for you all. I know I saw some questions that were Chem related. I think there might have been one organic question. Definitely check out that schedule. Go to the Chegg website and see what sources are available, and see what other office hours are available, so you can try to get your questions answered. Probably the last thing I would say to you all as you all are thinking about approaching chemistry, the more practice that you can do, the better. The more comfortable you get with doing these problems, the easier it will get. I promise y'all, it'll get easier. I joked with someone earlier about Chem. Chem was hard for me too, but I attended the office hours that my teacher would offer. I formed study groups with my classmates, and I found that as a great way to help me get through it. And so I promise y'all will get through it as well. And if not, Chegg is here to help you all along the way. And so we are just about out of time. And we are getting ready to wrap up. But I really appreciate all the engagement tonight. If you all have any additional questions, feel free to come to my page or to Chegg's page. Send us some questions for next week. We'll be back here. Actually, next week we will not be here. We will be off. I have an existing commitment. We'll be back in 2 weeks, but please feel free to reach out between now and then so that we can make sure we're answering as many questions as possible. And with that, we're going to get ready to wrap up, and I will see y'all in 2 weeks. But thanks so much for spending the hour.